Hi guys, my name is IBM. Greetings from Mongolia, and today I'm solving 970223 May June 2022. This is AS level structured questions. These are specifically Cambridge past paper questions. So without wasting time, I would like to take you to the question paper. So my student in India asked me to solve this particular paper because of a few questions. There were three questions. So instead of answering the three questions, I decided to solve the whole paper. So without wasting time, I'll go to the questions. I'll not go through the instructions. You can read through the instructions since you are even used to them. Okay, so question number one. A solid metal sphere has diameter 3.242 plus or minus 0.02 centimeters and a mass of 62 plus or minus 2 grams. Calculate the density in grams per centimeter cubed of the metal. So it is a sphere. Of course, we know the volume of a sphere. So density is equal to mass divided by volume. And of course, we know that the volume of a sphere is 4 divided by 3 pi r cubed. So if we consider radius to be diameter divided by 2, so it means where there is volume, so volume is going to be 4 pi over 3 into d over 2, but this is raised to power 3, which is going to be 4 pi d cubed divided by 3 times 2 power 3, which is 8. So this gives me pi d cubed over 6. So I will simply say density is going to be the mass divided by the volume, where the volume is pi d cubed over 3, so over 6, so the 6 goes up. And I remain with pi d cubed in the denominator, so this is going to be 6 times, we want the answer in grams per centimeters cubed, so I'll say 6 times 67 divided by pi times d, we want in centimeters cubed, so the diameter can remain in centimeters, so I'll say times 3.42, and this is raised to power 3. So I'll just press my calculator. 6 times 6.7, no, 6.6 times 67 divided by pi times 3.42 raised to the power of 3. So this is giving me 3.199, so approximately 3.199, which is approximately 3.2. Then determine the percentage uncertainty in the density. So we want percentage uncertainties. So since we have in the formula for density, we have 6m divided by pi d cubed. So 6 and pi are constants. I will ignore them in percentage uncertainties. But we see division and we see a power of d. So we shall use fractional uncertainties and change them to percentage. So absolute in density divided by rho is going to be absolute in m divided by m plus 3. Absolute in d divided by d. And of course, I'll multiply this by 100. This side also by 100 to get percentage uncertainty. So it means percentage in density on the left hand side is going to be m. M was 2 over 67 plus 3 times d, which is absolute is 0.02 divided by 3.42, and this is going to be times 100. So I'll press my calculator. 2 divided by 67 plus 0.06 divided by 3.42, then times 100, which is 4.74, or approximately 4.7%. Question 2. An archer releases an arrow towards a target at a velocity of 65 meters per second at an angle of 4.30 degrees above the horizontal as shown in the figure. Okay, so I'll just try to just prolong this first so that my calculations become very easy. So the direction of the arrow is this one here, and the speed in that direction is 65 meters per second. So we have a horizontal line here. I would draw a horizontal line. So it is released from this point. So I would draw a horizontal line here. Okay. So it means, of course, it means this angle is 65. I mean, this angle is 4.3. It is the same angle. If I draw a horizontal line here, this is 4.3 degrees. Okay. So if I resolve 65 to the horizontal, it will be 65 cos of 4.3 degrees. Let's see the questions. When released, the tip of the arrow is a horizontal distance of 70 meters from the target. That is, the horizontal displacement is 70 meters from the target and 1.66 meters above the horizontal. The arrow hits the center of the target. So the arrow hits the center of the target. Okay. Assume that air resistance is negligible, which means acceleration is going to be a constant, that is g. And this is actually going to be negative g because it goes slightly above the point of projection. And that all the mass of the arrow is at its tip. Show that the time taken for the arrow to reach the target is 1.0 seconds. Okay. So if I consider horizontal motion, I'm going to consider horizontal motion. And if I consider horizontal motion, I use S equals to UT plus a half AT squared. In the horizontal, S is 70. Initial velocity in the horizontal is going to be, we resolve this in the horizontal, so it is going to be 65 cos of 4.30 degrees plus, of course, acceleration in the horizontal is equal to 0 because there is no resultant force in the horizontal. The only force acting is the weight, which acts vertical downwards, so it will be plus 0. Okay, so here I'm trying to find the time. Oh, there's a t here. This is 65 cos 4.3 times t plus 0. There's a t here because it's ut. So it means t is going to be 70.0 divided by 65 cos of 4.30. So 70 divided by 65 cos of 4.3, which is 1.0799, which is approximately 1.08 seconds as required. Calculate the height of the center of the target above the ground. Height of the center of the target. So first here I'm going to consider vertical motion because height is in the vertical, so I'm considering vertical motion. And if I use S equals to UT plus a half AT squared. So we want to calculate the height of the center of the target above the ground. So S is going to be initial velocity. I'm considering vertical motion. Remember, when I sort of resolve this in the vertical, it will be 65 sine of 4.3. So U is going to be 65 sine of 4.3, then times the time. Of course, the time is 1.08. Then, because it moved against gravity, acceleration is going to be negative g. So it will be minus a half times 9.81 times t, which is 1.08 squared. So I'm finding the vertical displacement. So S is going to be equal to 65 sine of 4.3, then times 1.08, then minus 0.5 times 9.81 times 1.08 squared. which is negative 0.46, negative 0.46 meters. So the negative is showing that it actually in the vertical it falls below the point of projection. So the negative means, so it falls below the point of projection. So it falls 0.46 meters below the point of projection. It falls 0.46 meters below the point of projection. But remember, the point of projection was 1.66 meters above the ground. So we want to find the height. So the height from the above the ground, the height is going to be equal to 1.66 minus 0.46. So 1.66 minus 0.46, which gives us 1.2 meters. So this height is going to be 1.2 meters. Okay, so the height is 1.2 meters. By considering energy changes, state and explain how the final kinetic energy of the arrow as it hits the target compares with its initial kinetic energy after release. Any numerical calculation is not required. So how does the final kinetic energy of the arrow compare as it hits the target compare with its initial kinetic energy immediately after release? So we notice that it fell below the point of projection. That means the gravitational potential energy decreased. And if the gravitational potential energy decreased, there was a gain in kinetic energy because the speed was increasing. So in other words, the speed with which it hits the target is higher than the speed with which it is projected. So it means the total kinetic energy is conserved, must be conserved, or since total energy must be conserved, then the kinetic energy must be increased since there has been a decrease in the gravitational potential energy. So falling below the point of projection means gravitational potential energy has decreased. Gravitational potential energy decreased. But because total energy must be conserved, since total energy must be conserved, kinetic energy increased. So that means the final kinetic energy is greater than the initial kinetic energy. So final kinetic energy is greater than the initial kinetic energy. As simple as that. Question number 3, define velocity. We said velocity is the rate of change. Remember to add change in your answer. Rate of change of displacement. That is velocity, the rate of change of displacement. A constant driving force of 12,400 newtons acts on a car of mass 1,200 kilograms. The car accelerates from rest. That means initial velocity is 0 in a straight line along a horizontal road. Assume that resistive force is acting on the car negligible. That means the acceleration is constant. Calculate the acceleration of the car. If the acceleration is constant, then we shall simply use F equals to m times a, which means the acceleration is going to be the force divided by the mass, which means this should be 2,400 divided by the mass, which is 1,200. I think this is just 2 or 2.0. On the figure, sketch a graph showing the variation with the t of the velocity v of the car for the first 20 seconds of its motion. First 20 seconds, velocity against time. This is a constant acceleration. So the first 20 seconds, notice that the acceleration is 2 meters per second. So the first 20 seconds, it means final velocity v is equal to u plus at. It started from rest, so the final velocity is going to be acceleration, which is 2.0 times t, which is 20. So the final velocity should be 40 meters per second after 20 seconds. So this is going to be a straight line because the acceleration is constant, but stops at 40. So I would draw a straight line that stops at 40. This is not very good. Okay, so I'm aiming at this point here and from the origin. So they said label this line A. So this is going to be line A. That is A. In reality, a resistive force due to air resistance acts on the car in B. This resistive force increases with speed. So the force increases with the speed until it becomes equal in magnitude to the driving force at t equals 12 seconds. So at t equals 12 seconds, the driving force is equal to the viscous force. That means the acceleration is going to be 0, which means the speed becomes constant at t equals to 12 seconds. Okay. On the figure, sketch a second line to show the variation with the time t of the velocity v of the car for the first 20 seconds of its motion. Label this line B. Since there is air resistance, it means number one, the acceleration decreases and will always be less than the acceleration of shown by the previous graph. So I know that at around 12 seconds, it should become a horizontal line. So I'll draw a curve or a line below which starts at the same point, but it is always below the first one, and then it becomes a horizontal line at 12 seconds. So at 12, I should draw a horizontal line. So at 12 seconds, we reach what we call terminal velocity, so the line becomes horizontal. The velocity is going to be constant. They said label this graph B. Okay. At time t equals 20 seconds, driving force is increased to 3,000 newtons and remains constant at this value. Describe how the velocity of the car changes due to this increase in the driving force. So the driving force is increased to 300 newtons at t equals to 20 seconds. It is increased to 300 newtons. So that means the car will have an acceleration to a new but a higher terminal velocity, because initially um, the driving force was 2,400 newtons. So it means now it is going to be accelerated to it is going to have a new acceleration to a higher and to a new acceleration, and it's going to have a higher terminal velocity. So the car will have an acceleration to a new and higher terminal velocity. because the driving force has been increased, it means the air resistance must, or the resistive force should increase, will take more time to reach the higher driving force. And if it takes more time to reach the higher driving force, it means it will also gain more speed. So it will be, the car will have an acceleration to a new and a higher terminal velocity this time. Because they said the driving force is increased to 3,000 and remains constant. Describe how the velocity of the car changes due to this increase in the driving force. In reality, there is a resistive force. So they have not mentioned that the resistive force, okay, the resistive force increases with the speed until it becomes equal in magnitude. So here, because the driving force has been increased, it means from F, driving force should be equal to the viscous force for the air resistance to be bigger. And since the driving force is now bigger, it will also require a much higher resistive force. It will also require a much higher resistive force to balance it. And remember, the resistive force is directly proportional to speed squared, or it depends on the speed. A much higher resistive force means that the speed is going to be higher, so it means terminal velocity is going to be higher. Or you would simply say that the velocity will increase to a new terminal velocity. The velocity will increase to a new terminal velocity. Okay, as simple as that. The acceleration, the car will accelerate to a new and a higher terminal velocity, or we say the velocity will increase to a new terminal velocity. As simple as that. Question 4. A mass m moves a vertical distance delta h in a uniform gravitational field and gains gravitational potential energy delta EP. The acceleration of free fall is g. Use the concept of work done to show that the change in gravitational potential energy is equal to mg delta h. Okay. So we're using the concept of work done. So we know that work done equals to the force times distance in the direction of the force. The force has been given as, okay, we don't have the force here. So the force in this case is going to be the weight, which is going to be mg. And the distance in this case is going to be the vertical height, which is going to be delta h. So the work done is going to be mg delta h, but work done is equal to the gain in gravitational potential energy, but the work done equal to the gain in gravitational potential energy. Hence, the change in gravitational potential energy is going to be mg delta h. As simple as that. This statement here of saying that work done is equal to gain in gravitational potential energy is very important. You don't just equate randomly. A 0.6 kilogram mass is attached to a string which is wrapped around the wheel of a generator as shown in the figure here. The mass is held stationary above the floor. When released, the mass initially accelerates, then falls at a steady speed and spins the wheel. The generator causes a current in a resistor. Air resistance is negligible. That means acceleration is constant. State the main energy changes when the mass is falling at a steady speed. Steady speed means we cannot talk about gain in kinetic energy, because kinetic energy here is constant. KE is constant here. But they said initially accelerates and then falls at a steady speed. So that means since it falls, there is a change in height. So gain, there is gravitational potential energy. Gravitational potential energy is being lost, so gravitational potential energy changes to the generator causes a current in a resistor. So if there's a current in a resistor, the gravitational potential energy must be changing to heat or thermal. It's the same thing because the speed is constant, so there is no gain in kinetic energy. So the gravitational potential energy must most likely be, because heat is the final fate of all energy transformation. So there is gravitational potential energy, which is converted to heat and current. When falling at a steady speed, the mass in B falls falls a vertical distance of 1.4 meters in a time of 4 seconds. This causes a current of 90 milliamperes in the resistor. The resistance of the resistor is 47 ohms. Actually, the rate of work done by the mass. So rate of work done is power. So we know that power is equal to work done over time taken, where work done is the gain or the change in gravitational potential energy. Then this is divided by time, which is mg times change in height. We divide this by t. Or you can use force times velocity. So power is going to be equal to m, which was, what is m? The mass is 0.6. So this is going to be 0.6 times 9.81. Then h is 1.4. Then the time is 4.0. So I'll just press my calculator. 0.6 times 9.81 times 1.4 divided by 4. So this is giving me 2.06 or 2.1. So this is 2.1 watts. Then the power dissipated in the resistor. So power dissipated in the resistor is given by I squared times resistance. You can use I times V. You can use the other one is V squared over R, any of those. Okay, if I use the first one, power is going to be equal to I, which is 90 milliamperes. 90 milliamperes, I think, is 0.09. So I is going to be 90 times 10 to the power of minus 3, but this is squared, times the resistance, which is 47. Or you would say I, which is 90 times 10 to the power of minus 3, times V, which is, what is V? Okay, you could find V from I times R. So times V, which is I times R. That is still almost the same thing, which is I, which is 90 times R, which is that. So I'll just check the first one. You can finish the second one. So this is going to be 90 exponent minus 3 squared times 47, which is 0.38. So the power is 0.38. Then efficiency of the generator. So we know that efficiency is equal to power output divided by power input. Then we multiply this by 100 to make it percentage. If we want the answer in percentage, so this is going to be the power output is 0.38, which is the electrical. But the power input is the rate at which work is being done by the falling mass, which was 2.1. Then I multiply this by 100 if I want the answer to be percentage. So this is 0.38 divided by 2.1. Either I have 0.18, or if I multiply this by 100, it would be 18%. So the efficiency is going to be 18% or just 0.18. Okay, so I think that is all. Question 5, I think this should be waves. While light rays from the sun are incident normal on a magnifying glass, the magnifying glass directs the light to an area A of radius r as shown in the figure. The magnifying glass is circular in cross-section with a radius of 5.5 centimeters. The intensity of the light from the sun incident on the magnifying glass is 1.3 kilowatts per meter squared. Assume that all of the light incident on the magnifying glass is transmitted through it. Calculate the power of the light from the sun incident on the magnifying glass. Power. So know that intensity equals to power over area, which means the power is going to be intensity times the area. So the intensity is 1.3 kilo. So that is times 10 to the power of 3. Then the area is, we have the radius, so area is going to be pi r squared. So this is going to be pi times 0.055 squared, because this one is 0.055 in meters. So we have 1.3 exponent 3 times pi times 0.055 squared. So this is giving me 12.3 or 12.4. So the power is 12.4. Then the value of R is 1.5 millimeters. Capture the intensity of the light on area A. Okay, so still intensity is equal to power over area. Of course, the intensity is remaining, the power is a constant. So the power is going to be 12.4 divided by the area. They've told us now the radius is this. So remember, area is going to be pi r squared. So this is going to be pi times the radius, which is 1.5 times 10 to the power of minus 3, and this is squared. So we have 12. I'll start from the denominator, that is pi times 1.5 exponent minus 3, but it is squared. Then I get 12.4 divided by the answer. So this is 1.75 times 10 to the power of 6. So this is 1.75 times 10 to the power of 6. If you use the 12, you could get 1.7. So this is approximately 1.75 times 10 to the power of 6 watts per meter squared. If I use power as 12.4 instead of 12. A laser emits a beam of electromagnetic waves of frequency 3.7 times 10 to the power of 15 Hz in a vacuum. Show that the wavelength of the waves is 8.1 times 10 to the power of minus 8. So this is laser, so we don't need to know the speed of light. We don't need to be told the speed of light. So we know the wavelength is going to be V over F, which is going to be the speed of light divided by the frequency. That is 3 times 10 to the power of 8 divided by the frequency, which is 3.7 times 10 to the power of 15. 3 exponent 8 divided by 3.7 exponent 15. So this is 8.1 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. Power minus 8 meters as required. State the region of the electromagnetic spectrum to which these waves belong. Okay, so remember Rumenera's or Reed's mother is visiting Uncle Xavier's garden. Here we have visible light, which ranges from 7 times 10 to the power of minus 7 meters. And this side we have 4 times 10 to the power of minus 7 meters. So minus 8 is on the left, on the right hand side of the visible light. Minus 8 is the because the wavelength decreases. When I move from radio waves to gamma rays, here wavelength is decreasing. So it means 8.1 times 10 to the power of minus 8 meters just after violet. So it is ultraviolet. So this is ultraviolet. violet. The beam from the laser now passes through diffraction grating with 2400 lines per millimeter. So that means the number of lines per meter is going to be 2400 times 1000, because 1 millimeter has 2400 lines. Then how about 1 meter? So we multiply by 1000. A detector sensitive to the waves emitted by the laser is moved through an arc of 180 degrees in order to detect the maxima produced by the waves passing through the grating as shown. Calculate the number of maxima detected as the detector moves through 180 degrees along the line shown in the figure. The number of maxima, of course, when n is maximum, for any maximum, theta should be 90 degrees. So whenever you say diffraction grating, the first thing to come into your mind is d sine of theta is equal to n times lambda. And remember, d, that is the slit separation, is equal to 1 over n. And we have said this is going to be 1 divided by 204, 2400,000. Okay, but remember, for n to be maximum, theta should be equal to 90 degrees, which makes sine theta to be 1. So I'll simply say that n times wavelength, which is 8, I think it is 8.1 times 10 to the power of minus 8, should be equal to d, where there is d, I'm putting 1 over 2400,000, 400, then times 1000, then times sine of 90, which is 1. I'll first find n here. So 1 divided by 2400,000. Then I divide this by 8.1 exponent minus 8. So this is 5. We round off to the smallest whole number. So n is going to be 5 here. But the question is, because it is moved through 180 degrees. So we expect the central bright fringe. We expect n equals to 5 and n equals to 5 the other side. So the total is going to be 5 plus 1 plus 5, which is equal to 11. So the answer here is going to be 11, because as we move from the upper part, you notice the maximum to be fifth order. You go to the central order where n equals to 0. Then you go to the other side, you reach the fifth order. So it is 5 plus 1 plus 5, which is 11. The laser is now replaced with one that emits electromagnetic waves with a wavelength of 300 nanometers. Explain without calculation what happens to the number of maxima, that is n, detected. Assume that the detector is also sensitive to the wavelength of electromagnetic waves. So what has happened here? Remember, n lambda is equal to d sine theta. The laser is replaced with one that emits wavelength of 300 nanometers. 300 is 3 times 10 to the power of negative 7 meters. So the wavelength has been increased. Remember, wavelength is inversely proportional to n. So n should decrease. So I'll simply say the wavelength has increased. The wavelength has increased. The wavelength has increased, so the number of maxima decreases. So since the wavelength has increased, the number of maxima decreases. Okay. Question 6, I think, is electricity. On the figure, sketch the IV characteristic of a filament lamp. Of course, we know that I think this is where many of us make mistakes. So I'll just show you how this should look like. think this is not good enough. So it would appear as if it is a straight line at the center. Let me use a ruler first. Okay, but then remember, as temperatures, as V increases and as current increases, the temperature increases, so the resistance increases. So the line should curve at the end. Okay, so I'm trying to avoid to make this one perfectly horizontal, because if I make it perfectly horizontal, it gives an impression that the resistance has already reached infinity, yet we can't really determine infinity, so it is hard to make it bend. But if you are sketching on a paper, it is easy. You don't just make it perfectly horizontal, but you just show a decreasing gradient. Okay, so it is something like that, decreasing gradient at the extreme end. Let me draw this using a free hand then. So I want to draw something like this. Okay, I think that is better. But just avoid making this perfectly horizontal. Okay. Explain the shape of the line in A Roman 1. Okay, let's explain the shape. So of course we notice that as V increases, the current increases, but of course we know as I increases, the temperature increases. So I'll simply say as I increases, the temperature of the filament increases, and as temperature increases, then the resistance, of course, the resistance, if temperature increases, then the resistance of the filament increases, because resistance is directly proportional to temperature. So, and as temperature increases, and as temperature increases, I want to remove this comma here. And as temperature increases, the resistance of the filament increases. So the graph curves. So the graph is going to curve, because the ratio R is equal to V over I. So the ratio V over I increases, or you say the ratio I over V decreases. So the graph curves because the ratio because the ratio I over V decreases because R is V over I, or it is from the gradient, it is going to be 1 over the 1 over I, or 1 over V over I. So the ratio I over V decreases, or you would say V over I increases. As simple as that. So here you don't just say as V increases, I increases. You notice that here for this, we know that the resistance at any one point here is going to be 1 over I over V. So the ratio I over V decreases, which means the resistance increases. Or the ratio V over I increases, which means the resistance increases. A conducting wire has length 5.8 meters, cross-sectional area 3.4 times 10 to the power of minus 8 meters squared. The resistance of the metal wire, resistivity of the metal wire is 5.6 times 10 to the power of minus 8 meters. Calculate the resistance of the wire. Okay, so of course we know that resistance is equal to rho L over cross-sectional area. So they gave us rho as 5.6 times 10 to the power of minus 8. They gave us L as 5.8. They gave us the area as 3.4 times 10 to the power of minus 8. Okay, I'll just cross out the 10 to the power of minus 8. I'll say 5.6 times 5.8 divided by 3.4, which gives me 9.6 ohms. So this is going to be the resistance. A resistor of resistance R is placed in a circuit with a cell of negligible internal resistance. Okay. Two switches S1 and S2, a second resistor of resistance 2R, and 3 ammeters X, Y, and Z. The circuit is shown. The reading on X is 1.0 when switch S1 is open and S2 is closed. So when S2 is closed, X reads 1.0. This part will be out, Y will be out of circuit. When we close S2 here, the current in X is going to be the same as the current in Z. So Z will also read 1.0 when S1 is open and S2 is closed. So S1 is open and S2 is closed. So Z should also read S2 is closed and S1 is open. So Z should also read 1.0. Because Y, S1 is open, Y will not give a reading, so it will give us 0 here. Okay, I think that is fine. Complete the table. So let's see, open, S1 is closed. S1 is closed and S2 is open. So I'm assuming S2 is open here. S1 is closed, S2 is open. That means automatically Z reads 0. So let's check Z. Z is going to read 0. Z is going to read 0 when S2 is open. Z reads 0. Then how about X? Okay, let's check X. So remember, V equals to I times R. V is I times R. Then the resistance here is R. The current is I. So we want the reading in X and the reading in Y. When S2 is open, of course, the reading in X is going to be the same as the reading in Y. But what is that reading? So the resistance is R. So the current I is going to be V over R. What is V anyway? Let's check what is V. Using the previous part, when S2 was closed, V was equal to, in this stage here, when S2 was closed, V was equal to I times R V was equal to the current, which was 1.0, then times R, which was 2R. So it means V was initially 2R and V remains constant. The PD, total PD, which is the EMF of the cell, is constant, is going to be twice R. V is twice R. So it means in the second case here, because V is remaining the constant, the EMF is going to be 2R if I consider the first stage. Then the second stage, to find the current in X, I'm going to find V over R, where V is 2R divided by R, which gives me 2. So this is going to be 2.0. And of course, it is the same as Y, which is going to also be 2.0. In the third part, here, both of them are closed. So remember, V is the EMF, total V, which is the EMF, is equal to R. Okay, the EMF is 2R. I've got it from the second, where S1 was open and S2 was closed. So both of them closed, it means total resistance is going to be 2R times R over 2R plus R, which gives me 2R over 3. That is total resistance, 2R over 3. So if I want the total current, which is I in X, is going to be the EMF divided by total resistance. The EMF is equal to twice R divided by total resistance. Total resistance is going to be, so I will say times 3 over 2R, because I'm dividing, I get the reciprocal. So this gives me 3.0. So I in X is going to be 3.0 amperes. Then I in Y, because the current is going to be divided, so the current in Y is going to be the V, because these are in parallel, so the EMF is still the same, so it is going to be 2R over resistance of Y, which is R. So this is over R. So this is going to be 2.0 amperes, which means I of Z is going to be the EMF, which is 2R over resistance, which is 2R. This gives us 1 ampere. So this is going to be 2.0 and this is going to be 1.0. Okay. So that is the complete table. It requires a lot of understanding, of course. And finally, particle physics, which is always the last question. Fluorine 18 is an isotope that decays to an isotope of oxygen by the emission of beta plus. This is a positron. Calculate, complete the nuclear equation for the decay, including all the particles involved. So whenever beta plus particle is emitted, it is accompanied by another particle, which is because beta plus is an antiparticle, then the other one should be a normal particle, which is most likely going to be a neutrino. So this is going to give us oxygen plus beta plus. Beta plus is written like that, 0 plus 1. Then plus, this is going to be accompanied by a neutrino or an electron neutrino. So we balance this. So this should be 8 and this should remain 18. So I think that is the complete equation, which is balanced. Or you can add an E here to mean electron neutrino. A quark in fluorine nucleus changes flavor during the decay. State this change of flavor. So what has happened was that we have emitted beta plus. So what is happening if we have one more proton? We have emitted beta plus. Perhaps a proton has changed into a neutron. That is, proton is 1 1, neutron is 1 0 plus beta plus, which is 0 1. So it is like a proton has changed into a neutron. So it is like up, up, down has changed to up, down, down. So we can say an up quark has changed to a down quark. A hadron has a charge of -2e, where e is the elementary charge. State and explain whether the hadron is a meson or a baryon. This is automatically not a meson, because a meson can only have a charge of 0 or plus or minus e. So mesons can only have a charge of 0 or plus or minus E. So the hadron is a baryon. So the hadron is a baryon. So it can't be a meson because mesons have a charge of 0 or plus or minus E. So this hadron must be a baryon. Alternatively, you can say it must be made of 3 quarks as the largest negative charge is minus 2E. So it must be, or it must be it must be 3 quarks since the largest negative charge is minus 2 over 3e. That's the largest charge. So it must be 3 quarks since the largest negative charge is minus 2 over 3e. So a baryon. It is baryons which are made of 3 quarks. Then state a possible quark composition of the hadron. So we can try to check. If I say 3q equals to negative 2e, it means q equals to negative 2e over 3. So this is an anti-quark, which is either anti-top, anti-charm, or anti-up. So I will say 3 anti-up. So there are 3 anti-up quarks, or you can write anti-up like this. You can write 3 anti-top. You can write top anti-top like this. You can write anti-charm like this. Any of this is a correct answer to this question, or I can just say 3 anti-up quarks, 3 anti-top quarks, 3 anti-charm quarks, any of those. Not all of these. You just write one of them. I think that marks the end of this paper. And until next time, bye bye.